Hi everyone. Last week I posted a video on the introduction to the ECU and the controls and some of the things I do on the team. This video will be focusing on the Evo and the data acquisition as well as some of the background material like CAN and DBCs that are essential into understanding exactly what data acquisition is. So everything here will be mostly CCAR related as eCAR uses a vector to log data. Vector is basically a CAN listener like the Evo in just a separate way. But the principles regarding CAN should be the same, but when I talk about the EVO specifically, it determines to CCAR. If eCAR decides to go to the EVO, the knowledge will obviously be the same. So CCAR specifically has five main electrical units: the FEU, or the front electronics unit, I know, so aptly named, the steering wheel, the EVO, which is the main data acquisition device, the PDU, or the power distribution unit, formerly known as the REU, rear electronics unit, formerly known as Jacob Hoag's son, and the ECU, which is my son. So the front electronics unit is responsible for two key parts. It's backup power to APPS, so accelerator pedal position sensor has power from the PDU as well as the FEU. Sensor to CAN, so that's taking your analog sensor values and distributing it to CAN. And extra MOSFETs. We used to run a front anti-roll servo in the past, so we had a MOSFET up there to do that. We're getting rid of that MOSFET and we're getting rid of anti-roll, front anti-roll, or actual anti-roll controlled by servos this year. So we'll be getting rid of that MOSFET. So some of the CAN stuff. So why do we use CAN? So running analog signals over a distance can be prone to NVH, which is noise, vibration, harshness, or electromagnetic interference, or EMI. So we instead route sensors to the FEU, which then sends two CAN wires to the ECU and to the EVO. So instead of running a single wire for each sensor from the front of the cockpit to the back, we run all the wires to the FEU, or the front electronics unit, and we send two wires to the back, which are CAN high and CAN low. Since CAN has two wires, you'll only be asking, how do you transfer data of multiple different sensors with only two wires? So CAN stands for Controller Area Network and specifies the communication protocol and hardware requirements for systems using CAN. Each mini computer on the CAN bus is a node. So like the ECU is a node, the EVO is a node, the REU is a node, FEU is a node. These are all nodes on the CAN system. At the beginning of the first node and the end of the last node, you need a CAN termination resistor. It's a 120 ohm resistor that connects from CAN high to CAN low. So those are the hardware requirements. There's also some requirements with the length of the signal, since analog, digital, stuff like that. For the communication side, CAN is a string of bytes that is comprised of, to keep this episode simple, the ID and the value. So there's a much more priority bits that go into CAN, but for the purpose of understanding how the EVO works, the ID and the value is the most important part. So SAE J1939 is a standard that specifies which bits and bytes go where and what they are meant for, but the CAN IDs and the data values specified by us. So each sensor is given a CAN ID, which is the first two hex bits of the address, and the EVO or the ECU can use that to decrypt the sensor value for the right sensor. So let's say I have a phone over here. The phone here has a sensor A4, and I have some headphones over here, which is A5. So if I want to send, let's say a 1 is on, 0 is off. So I can do A51 and A41. So the ECU will say, okay, we're getting a message called A51. It looks up a file called a DBC, which is a database CAN, which maps your CAN IDs to the device. So it's like, okay, A5 is the headphones. The next bit is showing a 1, so it's on. So now it can decrypt that the headphones are on. Same thing as A40 means A4 means cell phone is off. So that's how all the sensors are able to communicate over those two wires. So there's a DBC file that is on the EVO and on the ECU, which correlate all these sensors to all the CAN IDs. Additionally, the PDU sends messages through CAN. So the PDU, again, is a power distribution unit, and it sends CAN messages for all the current values of each of the fuses. So we have E fuses, and we can do things like reset them, latch them, and some of the properties of that is we can take values and communicate them over CAN. So one of the things we can do is look at current values over time and log them, so we send those through CAN as well. And the basic part is that anything we want to listen to on the CAN network we run through the Evo. So the Evo is sitting there right in the middle, like a game of telephone almost. So you have a node here, data is getting passed through, and the Evo is just sitting in the middle, just kind of listening on both sides of the conversation and logging them over time. Um, So I will now explain the actual Evo system. So the AIM Evo 5. So the AIM Evo 5 is a little black box that sits right in front of the driver, right below the steering wheel. And it's responsible for collecting data and as a result, validating design decisions, checking lap times, making drivers better. It's very important for that. So the Evo itself has onboard sensors like GPS, an accelerometer, and a thermocouple hub, which is very useful. So GPS is lateral longitudinal acceleration, accelerometer for pitch yaw, and a thermocouple hub, which we use to tap into different sensors anywhere. So anytime we want to measure temperature over time, we can plug into the hub, and we can stick the K-type thermocouple or whatever we want anywhere in the car. When it comes to learning more about the Evo system, there is a 221 wiring harness diagram that I will post a picture in the description below that tells you all the different sensor values. I will also put up the softwares in a bit to show you how those sensors are configured in the Evo. Basically, each pin on the Evo has a specific corresponding software parameters. So one might be 5 digital outputs, 5 analog inputs. So based on those, we connect certain sensors to that. So you can put a wheel speed sensor for the wheel speed input, stuff like that. And to start and stop logging, the Evo has Wi-Fi or USB functionality. So the card that kind of the umbilical cord of the car, the capacitor cable, has the Evo USB built right into it, so we can plug right into the Evo with that cable. We can also log and grab data using Wi-Fi as well, which is useful when USB decides to go on a trip to Hawaii. So software. There are two pieces of software that we use to configure and log information, respectively. So Race Studio 3 and Race Studio Analysis. Race Studio 3 is used to configure the Evo, the actual device, configure the CAN channels, change the units, modify the units logged. Yep. And we can select sensors we want to log here. So we can check boxes. Oh, we don't want this, etc. I'll show you in a second. And we can also see live values when the car is turned on. So as soon as the car is turned on, the screen will show up with all the values and reporting live values as the car is running. So your battery voltage will go up and down, your plenum map, etc., etc., etc. So I will open Race Studio 3 now. All right, here we go. So over here, this is the main screen, and this is the one I just named it like this because I was prototyping, but I will create better nomenclature going forward so it's easier to understand. So this is all the channels that we have in the Evo. So all these right here on ID on the left side correspond to a certain pin, except for sensors like acceleration, which means this is the onboard IMU. So all the channels and the RPM and the speed come from direct lines. So for example, if we look at our gear position, the gear position is you have your name here, it's an angle, the sampling frequency, we can change the total potentiometer travel to make sure that the sensor doesn't reach overflow and hit zero. We can choose how precise we want it, decimal degrees. This situation, we don't really care about it because we use a function to make it discrete and show us gear over time. We don't really need 4.5 gear, for example, so that's why that is there. We can choose the type of sensor. That's pretty cool. That. We have ECU stream. So this is all the CAN coming from the ECU directly. So there's a pins for digital output sensors that come directly to the Evo and also just CAN 3 from the ECU. This is all the CAN sensors that come in. We have our T-map sensor, APPS, throttle percent load, oil pressure, etc., etc. So these are defined in DBC files in the ECU and are sent over CAN. So all of these can be logged over time, which is why they're so useful. These are the thermocouple hubs that we use that plug into the Evo. I will look at the DBC files now. So this is the DBC file that I keep talking about. Or that's the Evo's way of doing it. Hello, mister. Alright, So this is kind of how the structure works is you have your CAN ID here. So this is a 10 CAN ID, this is your 70. So as you can see here for the first one, your PDU fuses are in fact CAN ID of 10. So you have your fuse 1, your fuse 2, fuse 3. So you have these eight little bits here that contribute to the current value of each fuse. So we have 8 fuses here. So as you can go on, you can see each value has a CAN ID and then the byte order. So we specify this so the evo can decrypt these messages. Let's see back here. I can also show custom sensors. So where's that? Yes. So Jacob Hogue created this. This basically maps our shock pot values correctly. So he calibrated it in, it's a 5-volt sensor, so 0 to 5 volt is the logic. As you can see here, 0 and then 5,000 millivolts. And each increment in, it's a linear potentiometer. So as you increase, the value increases, so on and so forth. So you can see the max travel here is 3 inches and minimum is 0 inches. So this is how you set up a sensor, for example. And it's a position, we can calibrate it auto, which means we can calibrate it on track. We can zero the value out to make sure that the values are both even, right and left. Okay, so now I will go over the analysis software. You can also click this button here to go to the analysis, but I'll just have it open here. So this is Ray Studio Analysis. Maggie is actually going a lot more in depth into driver training and the data required and stuff like that. I will just be going over the software basics of what are the certain buttons we use and kind of different sensors. So right here, for example, I have UVINS 220C generic testing. The comment here is as a skid pad coast down, so we always make sure to put a comment on it, maybe sometimes more descriptive so we know exactly what we're looking at in the future. I'll just double click that and I'll click open test. So on the left side here, you have a list of all your sensors. So these are all the sensors that are logged over CAN as I showed earlier, and a bunch of the onboard sensors, so your latitude acceleration, your longitudinal acceleration. So every time you click one, you can add it to the view here. So you can double click an axis to scale it properly. So if you want to see more in depth, you can double click it and it'll scale it. Also, you can look at the GPS data. Where is that? It doesn't want to show me. There's usually a GPS trace. I don't know why that's not working suddenly. But for example, here you can see, okay, here's vehicle speed. So one's pretty cool at. We have 0 to 300 miles an hour here. Unless we swap 13 rotary engines and 14 superchargers, I don't think we're going to get to 300 miles an hour. But we have here acceleration and skid down, coast down, acceleration. So you can see the car over time and use GPS speed to validate some of our measurements. We have here's temperature. So this is diff temp over time. We reach a peak of roughly 72 degrees right there. So basically, anytime we want to validate a design decision, we log it to make sure it's well. So someone wanted to know the temperature of the diff so we can properly account for how hot the monocoque is going to be since we're going to a full monocoque. So this is valuable data to know that in our testing, at least with the air cooling it, the diff gets to about 71 degrees Celsius. But keep in mind there's also hardware issues of where we mount the sensor falling off, sensor taking a trip, sensor getting cut, etc., etc. But it's valuable information to have nonetheless. We have wheel speeds here. So essentially these are just different values we log, and someone smarter than me can actually pick out UVIN's steering angle effort could be larger here, the throttle could be better here, brake could be better here. But comparing drivers on the same track is easier to look at. And hopefully I'll have a more concise video on driver training and data analysis coming up. But these are the kind of what the software is used. I think that should be it. All right. If anyone has any other questions, feel free to reach out to me for all the software, the Evo stuff, and any questions related to the analysis portion. Or if you're really interested in getting into driver feedback and reading data, that's Maggie's job. So feel free to reach out to her. Um, Thanks for watching.